We did look at this problem in class, looking at how the path is described to us as y is a function of x. That's a almost certainty that we ought to work that problem, y of x, in normal and tangential coordinates. And so what we have is an airplane flying a parabolic path. The equation of the path is given, and let's see what we're being asked to learn. The jet plane is traveling at a constant speed of 1,000 feet per second along the curve, with the equation y equal given, where x and y are in feet. If the pilot has a weight of 180 pounds, determine the normal and tangential components of the force the seat exerts on the pilot when y equal 10,000 feet. Now, looking at the curve, we don't know where on this curve y in fact equals 10,000 feet, and so if we will plug in y equal 10,000 to here, we'll be able to solve for the x that makes that true. So that's one of the first things we'll do. So plugging in 10,000, this is an x squared term. We're going to get two answers, but we'll take the positive one, and x equal 15,811 feet. Now, we are going to want to then draw a free body diagram of the airplane at that value of x. Now, clearly x is way out here somewhere, and our path does have an angle to it. So we're going to draw that angle into our free body diagram. And so here is our pilot. The seat will produce a normal force on the bottom of the pilot. The seat will produce a tangent force on the back of the pilot. The seats are lined up with the airplane, so the airplane traveling tangent to the path is traveling at some angle relative to the horizontal. The airplane is climbing. And so we're going to call this the tangent direction. And then toward the center of the circle, we must call up the normal direction, not down. And then, other than the seat forces acting on the pilot, we have gravity acting on the pilot, and that would be all. Now, one of the things we're going to need to do is find this angle between the horizontal and the tangent. Okay, and of course we understand that the tangent direction on a curve in 2D is directly related to the slope of the curve. As a matter of fact, the tangent angle is determined by the slope, and the slope of an equation expressed as form y of x is going to come from a derivative of y with respect to x. And so the derivative of y with respect to x is going to give us the slope, but the slope of any curve is the tangent of the slope angle. And so our derivative of a quadratic is going to be 2 times 20 times 10 to the minus 6x, plus that's all. The constant disappears. So 40 times 10 to the minus 6x. Plugging in x equal to 15,811, which is where the airplane is at right now, we come up with a slope of 0.63. That's a pretty good slope. That's and we come and take the inverse tangent, and we come up with a slope angle of 32.31 degrees, having done the inverse tangent. Now, if we're going to be summing forces setting equal to mass times acceleration in the normal direction, we know that that's equal to mv squared over rho. We will need v squared, but we're told we're flying at constant speed, but we are going to need rho. So going to the equation sheet, and I don't have that handy, so the equation sheet in fact says 1 over rho is equal to the reciprocal of this equation. It doesn't show this directly, but we need dy dx, and we need d squared y dx squared. We already have dy dx. We got that when we did the slope calculation, but now we need to take one more derivative, the second derivative of y with respect to x, but the first derivative was a constant times x, so the second derivative is just going to be that constant, 40 times 10 to the minus 6. Then plugging both the slope and the second derivative into the curvature equation, we come up with a radius of curvature of 41,411 feet. It's a fairly large radius of curvature. Now we're ready to take everything we have, plug it into sum of forces in our normal direction is equal mass times acceleration in the normal direction is equal to mv squared over rho. And our forces in the normal direction, looking at the free body diagram, will only be the normal seat and the force in the positive direction, and our component of gravity in the negative normal direction. And so we have the seat force minus 180 cosine of the 32.3 slope angle degrees is equal to mass 180 over 32.2 times v squared. We were told it was traveling at a constant velocity of 1,000 feet per second. Is that true? Yes, feet per second, so that's the right units, divided by rho, which is 41,000 feet. One equation, one unknown. Normal force in the seat, 287 pounds. So the 180-pound pilot feels like he was weighing 287 pounds. Then we can do the same thing, calculating the forces in the tangent direction, equal mass times acceleration in the tangent, but since we're traveling at constant speed, that acceleration in the tangent is 0, and so the right-hand side is 0. And so our forces in the tangent direction, if we look at it, would be the back of the seat force in the positive tangent and a gravity piece in the negative tangent direction. And so we have the tangent seat force minus 180 degrees sine of the slope angle is equal to mass times acceleration, which is 0. And so again, one equation, one unknown. Solving for the tangent force out of that one equation, we get a tangent force of 96.2 pounds, substantially smaller than the force from the bottom of the seat.